I have to ask you another follow-up question about this shut up and calculate phenomenon about mathematical objects. This current physical system that we have can be ascribed by a mathematical object known as a wave function. There are different schools of thought around the significance of it. There's a school of thought that says the wave function is just representational of a physical structure. There's another school of thought that says the wave function itself is fundamental, or mathematical objects or structures are fundamental. This is something Max Tegmark also talks about. The universe is mathematical.
Mm-hmm.
There's cubism, there's number theory, there's Einstein's interpretation of these being statistical averages. Where do you stand on this? Do you think mathematical objects are fundamental in nature? Are they representation of physical structures, or is there something else entirely?
Well, mathematical physics is a field where mathematics is used as a representational tool, right? As a piece of language, if you will. Yeah. I'm going to use mathematical objects in an attempt to represent the physical world. Yeah. And those mathematical objects can be used in lots of different ways. So there's not one single answer to what does this piece of mathematics indicate about the physical world. If you just open up a physics textbook, you have to then look in great detail, where did this mathematical object come from? Yeah. Sometimes, as Einstein, as you say, wanted to understand the wave function statistically, that it's a kind of representation, sure, but it's a representation fundamentally of large collections of systems and telling you about their statistical characteristics, right? A certain percent are like this, a certain percent. This is what happens in thermodynamics. Yeah. We understand how to do that. And then you say, okay, so this mathematical object is not a representation of any single system. It's a representation of a collection of systems. And if I take this single system and move it from this collective to this collective, a different representation might be relevant now because I'm actually looking at a different statistic. That's the way Einstein wanted to think about the probabilities in quantum mechanics. So that's the so-called statistical interpretation. Mm-hmm. I can't make head or tail out of Max's idea that fundamentally physics just is mathematics, and every mathematical object is a physical object, and every mathematically representable possibility is a real physical world. As if, yeah, there is a real physical world somewhere that's Newtonian, because you can write down Newtonian mechanics as some differential equations. I can't make it. I mean, just can't make head or tail out of that. There's some objects or elements of physics that we represent mathematically, and we think it's because they actually have a physical structure which is being very directly represented by the mathematics. So Euclidean geometry is a perfectly clear, abstract mathematical structure. You can ask all kinds of questions about objects in Euclidean geometry and get, really surprising answers. The example I always like is the one that Kant used, actually, is that something that Euclid proves is that if you take a circle and put any two chords in it that intersect, so I'm just going to draw some straight lines across it, but they have to intersect.
Yep.
So this line gets cut into two pieces. This line gets cut into two pieces. Now, from these two pieces make a rectangle. From these two pieces make a rectangle. Those two rectangles will always have the same area. And you're going, wow, that's cool. That's a fact about Euclidean geometry. Does it follow that anything in the physical world has the structure postulated by Euclidean geometry? No, it doesn't follow at all. We know that at macroscopic scale, the space we are moving around in is pretty close to being Euclidean. We know that because we use Euclidean geometry to do surveying calculations, and it works really well. Doesn't mean it's perfect, right? There could be deviations at very fine levels. So there's something in the physical world that is very nearly well represented, at least by Euclidean geometry. Maybe there's something in the world that's exactly represented by Euclidean geometry. That would be interesting. And that would immediately explain the utility of Euclidean geometry in doing physical things. Or maybe the world is not fundamentally Euclidean at all, but there's an explanation for it has a structure that is in some well-defined sense close to Euclidean, at least at everyday scales, right? That would make sense. To say that physical space is just a mathematical object, to me, that doesn't make any sense, right? It may have a structure that's well represented mathematically, but that's different from saying it is simply a mathematical thing. So I would take that off the table.